Hello chemists and welcome back for lesson 3 of our series on crude oil. In this lesson we're going to be looking at cracking. Make sure you've watched videos 1 and 2 before attempting any of this content. So to begin with, we're going to do a little recap task on what we've studied before. You know the drill by now, so please pause the video, attempt the questions and then come back to check your answers. For things like definitions, your answers do need to be exactly the same as mine. Please don't go away and try and copy some random degree level response off of the internet. Okay, so the process used to separate crude oil is called fractional distillation. The definition of crude oil is that it's a mixture of compounds called hydrocarbons. The definition of a hydrocarbon is a compound made from hydrogen and carbon atoms only. The hydrocarbon can be called an alkane if it satisfies these criteria. So all of its carbon-to-carbon bonds need to be single covalent bonds, and its formula must abide by the general formula of CnH2n plus 2, which means that the number of hydrogen atoms is twice that of the number of carbon atoms and another 2. The relationship between chain length of a hydrocarbon and boiling point is that the longer its chain length, the higher its boiling point will be. So the higher the temperature you would need to evaporate it. The relationship between chain length of a hydrocarbon and its viscosity, well, remember that viscosity means like thickness or gloopiness. So again, the longer the chain length, the higher the viscosity. The relationship between the chain length of a hydrocarbon and its flammability, though, is inversely proportional in the fact that the shorter the chain length, the more flammable it will be, so the higher the flammability. And next up, we've got a word fill exercise on describing and explaining the process of fractional distillation. So have a really good read of this and see what words you can get to fit in the gaps, then come back to check your answers. So the first stage in fractional distillation is that the crude oil is heated until all of the hydrocarbons evaporate. The vapour is then pumped into a column or a fractionating column, which gets cooler towards the top. The longest chain lengths have the higher boiling points, so they'll condense near the bottom of the column. The shorter chain lengths, however, have lower boiling points, so they need to be cooled down more in order to condense them. Therefore, what they're going to do is condense nearer to the top of the column, where it's cooler. This separates fractions of crude oil, which are smaller submixtures with more similar chain lengths and boiling points. These fractions are then drawn off and stored separately, therefore the crude oil has been separated. Now, what we're going to do is look at the percentage of crude oil that goes to make each fraction. So remember that we've taken the crude oil mixture and we've carried out the process of separation using fractional distillation. And that's provided us with a range of different fractions, smaller submixtures with similar chain lengths of the crude oil. Now, if we actually have a look at the percentage of the total of crude oil that goes into each fraction, you can see it in this table here. Now, this isn't true for every sample of crude oil around the world, and this is likely to vary depending on where the crude oil has been extracted. So you can have a different ratio of each fraction depending on where that crude oil has come out of the ground. I've plotted this to a graph as well, so you can see it a little bit like this. Some of you more eager out there might notice that we've got naphtha this time. Naphtha isn't exactly a fuel. Naphtha is used in chemical feedstock, so that means that other chemicals are made from naphtha. It's still a very useful fraction. So we can see the percentages of each fraction as a total of the crude oil sample here. Now, these fractions highlighted here with the green ring around them are actually very useful and they're in quite high demand, and that's because all of these can be used for fuels. Whereas this fraction here, bitumen, which I've highlighted in the orange circle, is not as useful and it's in quite low demand. But you'll notice that there's actually quite a high supply of it, whereas these more useful or high demand fractions, there's a relatively lower supply of each of those. So we're facing a little bit of a problem here. Let's have a look at the supply versus demand for each fraction. So I've repeated the chart here, and just to mention again that these are more useful, and those nearer the top have got the shorter chains and those nearer the bottom have got the longer chains. These are the most useful because they're the best fuels, really. The problem with these is that there's a very low supply of them. You can see that after we fractionally distill the crude oil, you're getting a very small percentage of the crude oil is actually these very useful fractions. But we've got a very high demand for them. Now, we've got high demand for these very shortest chain lengths because they've got low viscosity and higher flammability, which makes them really, really great fuels. Whereas things like bitumen, we've got a very high supply of them. Almost 40% of crude oil is bitumen, but it's not as useful, so it's in very low demand. And this is because the longer chain length means that it's more viscous and it's less flammable. So it makes a terrible fuel, because something that's not very flammable and something that's so thick that it would block up the pipes of an engine wouldn't be a very good fuel. What we need is a method that could convert these longer chain lengths, like bitumen, that are less useful and in low demand, into the shorter chain lengths, like these up the very top here, that are more useful because they're much better fuels. We need a method to turn those longer chain lengths into shorter chain lengths. And we have that method. And that method is called cracking. So let's have a look at what cracking does. Cracking is a method of breaking the bonds in long chain hydrocarbons to produce shorter chain hydrocarbons. And typically this is done on the fractions which have long chains to make them into fractions that have shorter chains. Our justification for this is as follows. The shorter chain lengths are in greater demand than the supply gives us. Because the shorter chains are better fuels, and remember that they're better fuels because they're more flammable and they're less viscous. So where does cracking fit into our timeline? Well, we took the crude oil mixture, we carried out fractional distillation to separate it out into its useful fractions. We got the useful fractions here. The shorter chain lengths were really useful as fuels and for making different chemicals. We call that chemical feedstock. Whereas our longer chains needed to undergo cracking to produce shorter chains. So then they can be used as fuels or chemical feedstock. So we can see here, cracking is carried out after fractional distillation on the very longest chains, which aren't very useful and are in low demand. And it makes them into the shorter chains, which are in higher demand and are more useful as fuels. So let's now have a look at the process of cracking. So we're going to have a big reactor that cracking's carried out inside, and there's either going to be one of two different types of cracking carried out. The first type of cracking which we look at is called catalytic cracking. I couldn't really think of an image to represent a catalyst because they all look a little bit different, but I've shown it like this because catalysts typically have a very high surface area. They're almost like a honeycomb structure, which helps to increase the rate of reaction. Now, the conditions for catalytic cracking are as follows. You need a high temperature and you need to use a catalyst. And those of you that remember from the rates of reaction unit that you should have studied before this, a catalyst is a substance which speeds up the rate of a chemical reaction, and it does this by providing an alternate pathway with a lower activation energy. Remember that activation energy is the minimum energy for a reaction to start, and if we do a reaction with a lower activation energy, you can do it at a lower temperature, so it saves you a bit of money in terms of cost there for energy bills. But it also makes the reaction go faster, so you're forming that product more quickly. So all good efficiency measures there. Alternatively, we could carry out a type of cracking called steam cracking, and the conditions are very similar for steam cracking and catalytic cracking. You also need a high temperature, but this one, instead of using a catalyst, it just uses steam. Now, because both of these use a high temperature, that indicates that cracking is actually a type of thermal decomposition. You should have come across this type of reaction before in Key Stage 3. And you should remember that thermal decomposition is any reaction that uses heat to break bonds. So some questions for you here. If you could pause the video, read and attempt the questions, and then come back for the answers. So the fractions of crude oil which are not very useful, and a reason for this, are any fractions with long chains, for example bitumen, and they're not useful because they have low flammability and high viscosity, making them poor fuels. The fractions of crude oil which are useful are the fractions with short chains, like natural gases and petroleum, and they're useful because they have very high flammability and low viscosity, meaning they make great fuels. The process of cracking is carried out. Let's have a look at why. So remember that we've got our short chains which make better fuels are in high demand but low supply. And our long chains which make poorer fuels are in high supply but low demand. So cracking breaks the bonds in the long chains to produce the shorter chains to help meet that demand for the more useful short chains. And where does cracking fit into the stages of crude oil processing? Well, cracking is carried out on the long chain fractions following or after fractional distillation. Some more questions for you now. Pause the video, attempt, and then come back. So the two types of cracking and their conditions. The first type of cracking is called catalytic cracking, and it uses a high temperature and a catalyst. The second type of cracking is called steam cracking, and it uses, again, a high temperature and steam. The type of reaction that cracking is, and an explanation for this, is that it's a thermal decomposition reaction as it uses heat to break the bonds. Remember, breaking the bonds in those long chains to form those short chain hydrocarbons. Let's describe a catalyst. A catalyst is a substance which speeds up the rate of a reaction. You might have also said that it doesn't get used up. That's also true. And it helps to speed up the rate of reaction by providing an alternate pathway with a lower activation energy. Key fact for you as well, remember that catalysts don't only speed up the rate of reaction, because they allow the reaction to proceed with a lower activation energy, you can carry out that reaction at a lower temperature, which if you're a chemical industry, saves you a lot of money on heating. Let's have a definition of the activation energy now. It's the minimum energy required to start a reaction. Emphasis there on the word minimum. Let's now have a look at the product that cracking produces. So we said earlier that cracking breaks the bonds in long chain hydrocarbons, and in doing so it makes short chain hydrocarbons. But we can give a little bit more detail on actually what's going on here. So let's take a long chain hydrocarbon with the formula C18H38. So it's got 18 carbon atoms all in a big chain. When we carry out the process of cracking, this forms multiple different products, which I've shown here. Now, if we have a look at the formulae of these products, we might be able to give a little bit more information about their identity. So let's have a look at this first one, C6H14. Now, 14 could be made by doubling 6 and adding 2. And you should have come across this idea before in the previous lessons. So if we were to write this thing's general formula, we can say that it abides by the general formula of CnH2n plus 2, meaning that the number of hydrogens is twice the number of carbons and another 2. So because it follows this general formula, this means we're looking at an alkane type of hydrocarbon. Let's now have a look at the formula of these remaining 3. Well, in each of these, 8 is only double 4. It's not double 4 plus 2. 6 is double 3, and 4 is double 2. So these hydrocarbons abide by a general formula of CnH2n, meaning that the number of hydrogens is only double the number of carbons. It's not double the number of carbons and 2 like an alkane. If a hydrocarbon follows this general formula of CnH2n, then it can be classified as an alkene instead. So we can say overall that cracking, the process of cracking, not only produces short chain hydrocarbons, but those short chain hydrocarbons that it produces will be a mixture of alkanes and alkenes. So let's have a little look at some more information about alkenes, because it's not just their general formula of CnH2n which defines them. So yes, we can say that they will abide by the general formula of CnH2n, where n is the number of carbon atoms and 2n gives us the number of hydrogen atoms, twice the number of carbons. Another thing we can say about alkenes is that their names will all end in -ene. So we could have something like propene, and prop means 3 carbons and ene means it's an alkene. So we write 3 carbons, C3, and the number of hydrogens will only be double this time because it's an alkene, so we'll have H6. Now if we try to draw them, we might run into a little bit of an issue if we follow the rules that I gave you last time. So we can draw the 3 carbon atoms like this. Okay, so we've got 1, 2 and 3 because propene has 3 carbons as shown in the formula. Now if we just tried to bond all of these carbons in a line like we did previously and then add the 6 hydrogens onto this chain like this, then this does not follow the rules of bonding that carbon must abide by. Carbon must always form a total of 4 bonds. So in other words, you need 4 lines coming out of each carbon. You'll notice that this carbon in the middle here is fine. Look, 1, 2, 3 and 4. But these carbons on the end are not happy because they've only formed 3 bonds. Look, 1, 2 and 3, 1, 2 and 3. So this representation of propene, although it fits the formula, it's wrong because it doesn't follow the bonding rules for carbon. Instead, what we have to do is make one of the carbon-to-carbon bonds a double covalent bond, and we represent that with 2 lines. It's not an equal sign, it's called a double covalent bond. So we're going to draw one double covalent bond, so this is one double covalent bond here, and then we're going to make the rest of the bonds in the chain that we need to draw single bonds, like that, as we used to do. So now, when it goes to adding the hydrogens, we've got to fit 6 hydrogens on, according to the formula. Well, this carbon, effectively, already has 2 lines coming out of it, 2 bonds, so we only need to add 2 hydrogens onto the end here, like that. 1, 2, 3, 4. This carbon's now happy. This carbon in the middle here, you can see it's already got 3 bonds, so 1, 2, and then the third there. So this one only needs 1 hydrogen, so we're going to pop the 1 on there. And then finally, this carbon here has only got 1 bond so far, so it needs to form 3 more bonds to hydrogen. So we're going to go 1, 2, and then 3. So if we now count the number of hydrogens, 1, 2, 3, 4, 5, 6, it matches the formula. And if we look at every single carbon in the chain, it's formed a total of 4 bonds. And we achieved that with the formula of C3H6 by putting a double bond as one of the carbon-to-carbon bonds. So we can say the third rule about alkenes is that they will always contain a C to C double covalent bond, or a carbon-to-carbon double covalent bond. Let's construct some more alkenes just to get those rules correct. Let's start with ethene. Eth meaning 2 carbons, ene meaning it's an alkene. So it'll have a general formula that abides by CnH2n. In other words, the number of hydrogens will be double the number of carbons. We'll draw our 2 carbons in a line, and then we've got to make at least one of the bonds a double covalent bond, and there's only 1 bond to make anyway, so we're going to make that the double bond. Then we need to add 2 hydrogens to this carbon because it's already made 2 bonds, 1 and 2, and 2 hydrogens to this carbon because it's already made 2 bonds, 1 and then 2. You can see this carbon's now got a total of 4 bonds, this carbon's now got a total of 4 bonds. We've got at least 1 C to C double bond, and it matches the formula for ethene. Propene next, which we've already done, so I'm going to skip through this one. And then finally butene. So we've got 4 carbons in butene, so I'm going to draw my 4 carbons in a line. And remember, I need to make at least one of those carbon-to-carbon bonds a double covalent bond. So I'm going to just do it on the first one. It doesn't actually matter where you do it in the chain, as long as you've got one of them. So I'm going to put it here. Now the rest of the carbon-to-carbon bonds are going to be single bonds, so I'll put them there. And then what we've got to do is add enough hydrogens to each carbon so that it's made a total of 4 bonds. So this carbon's already made 2 bonds, so it needs 2 hydrogens. Now it's got a total of 4 bonds. This carbon's already made a total of 3 bonds, so to get to 4 we only need 1 hydrogen. This carbon's made 2 bonds so far, so it needs 2 hydrogens. And this carbon has only made 1 bond so far, so it needs 3 hydrogens. Now, just a key tip here, because students always get this wrong. Remember, don't make all of the carbon-to-carbon bonds, so all of these along the chain, double covalent bonds, just do it with 1. Otherwise, it won't fit the formula that you're after, or the bonding arrangement of 4 bonds per carbon atom. So now we've had a little look at alkenes, let's just summarise them versus alkanes. An alkene will always abide by the general formula of CnH2n. It will contain a CC double covalent bond, just one of them at GCSE typically. And its name will end in ene, an example being propene. An alkane, however, will follow the general formula of CnH2n plus 2. It will only contain carbon-to-carbon single covalent bonds, like a single line between the carbon atoms. And its name will end in ane, for example, propane. So you can see that we've got propene and propane. Propene being an alkene with its general formula of CnH2n, propane being an alkane with its general formula of CnH2n plus 2, CC double bond in our alkene, only CC single bonds in our alkane. Now let's imagine that we had a test tube filled with a hydrocarbon and you weren't sure whether it was an alkene or an alkane, and you wanted to test to determine which it was. Well, there's a test that specifically works on alkenes, and it's called bromine water. And bromine water typically comes in a little stoppered bottle with a pipette stuck through the top so you can just lift it out and squirt the bromine water into whatever you want. Now, bromine water is orange. Key fact you need to know about it. So what we're going to do is take our test tube filled with our sample, which we are unsure of whether it's an alkene or an alkane, and we're going to add a few drops of our bromine water to it and give it a shake. Now, if that bromine water changes from orange to colourless, then an alkene has been identified. There is an alkene there. Let's have a little look. You can see the colour of the bromine water changed. It changed from orange to colourless. So that means in this test tube, we do have an alkene. It's very important that you say that changes orange to colourless, and you don't just say it turns colourless. You need to state the full change of the chemical test, not just the result. Alternatively, if you just popped that bromine water in and it remained orange, then there's no change from the colour of the bromine water, so therefore you're not looking at an alkene. Now, because you're adding the bromine water to the sample, what will actually happen here is the orange colour of the bromine water will almost shine through in the sample. So it will start turning progressively more and more orange as you add more bromine water, just because that orange colour is shining through. It's not saying there's been a change there, it's just that the orange colour of the bromine water has persisted, it's stayed there. So that means that you've had a negative result. There's no alkene present. So in this case, we're not looking at an alkene, we're looking at an alkane. Finally, let's look at equations for cracking. Typically in GCSE, what you're given is an equation and it's got a gap, and you're asked to write a formula in that gap, and you may also need to balance the equation. Here's an example of one. We've got a longer chain hydrocarbon, not that long, but it's longer, C10H22, so we'd call this one decane. And it's undergoing cracking, a type of thermal decomposition, and it's breaking down into C3H8, so that's actually propane, plus something, plus C5H10, that's actually pentene. So basically what we need to do is work out what the formula is of the compound that goes in this gap here. Now these are pretty straightforward to do. First thing we need to do is count the atoms of each element in the reactant, so that's the left of the arrow, and the product, so that's the right of the arrow. So here I've got 10 carbons, and here I've got 22 hydrogens. Now to get the numbers on the right hand side, I'm going to need to add everything up. So I've got 3 carbons here and 5 here, so that makes a total of 8. And I have 8 hydrogens here and 10 here, so that makes a total of 18. Next up, what we're going to do is find the difference between the numbers of atoms on the left in the reactants and the number of atoms on the right in the products. So you can see I've got 10 carbons on the left, but only 8 on the right. So I'm going to need another 2 carbons in whatever this thing's formula is in order to balance that out. And then I've got 22 hydrogens on the left, but only 18 on the right. So I'm going to need another 4 hydrogens on the right here. That's all one formula, not 2 separate things. I've stuck those together to make C2H4, which is ethene, by the way. Now we're going to just check to see that the equation is balanced. So now when I add up on the right, I've got 3 plus 2 plus 5. That gives me 10 carbons. So that's now balanced for the left and the right. And I've got 8 plus 4, so 12, plus the 10. So I've got 22 hydrogens in the products now on the right, so that's balanced for the reactants as well. Let's have a look at another example now. So we've got C14H30 undergoing cracking to form 3 of something plus C8H18. So again, what we're going to do is count the atoms of each element on the left in the reactants and the right in the products. So I've got 14 carbon atoms and 30 hydrogen atoms. I don't know what's here yet, but over here I've got 8 carbon atoms and I've got 18 hydrogen atoms. So we've got to work out what goes in this gap. So again, we're going to find the difference and use this to construct the formula, but I'm not going to write this formula straight into the gap this time because there's this 3 in front of it. So whatever I write here will be multiplied by 3. So I'm just going to write it over here for a minute. So the difference between the 8 and the 14 should give me 6. So I've got 6 carbons missing on this right-hand side. The difference between the 18 hydrogens and the 30 is 12. So I'm missing 12 hydrogens on the right-hand side. But because I've got this 3 here, whatever I put in this gap will be multiplied by 3. So I can't put this in the gap, otherwise I'm going to have way more carbons and hydrogens than I need on this side. So the next thing I'm going to do in this case is divide whatever this formula was that I worked out to be missing by the balancing number. So I'm going to divide this by 3. And that will give me the formula of C2H4. So now when I check that this equation is balanced, 3 2's give me 6 carbons, plus the 8 gives me 14. For the hydrogens, 3 4's gives me 12 hydrogens, plus the 18 gives me 30. So that's now balanced as well. Okay, final task then for today. So you've got a few questions, pause the video and then come back for the answers. Cracking produces a mixture of alkanes and alkenes. Sorry, alkenes and alkanes. Doesn't matter which order you write those in. Describe the features of an alkene. Well, it's going to follow the general formula of CnH2n. It will contain a CC double covalent bond and its name ends in -ene. We've got to draw pentene next, and to draw pentene you would have had to have worked out its chemical formula. Pent means 5, so we're going to have C5. Ene means it's an alkene. And if it's an alkene, because it follows this general formula of CnH2n, we're going to have twice the number of hydrogens as carbons, so pentene will have the formula C5H10. We can now construct it. So you should have got something that looked like this. Make sure that every carbon has a total of 4 bonds, so 4 lines coming out of it. And you've got 1 carbon-to-carbon double bond. Now, if you'd done some research in the background rather than trying to work it out for yourself, you might have drawn it with that double bond elsewhere along the chain. That is fine as long as it follows those 2 rules that I just described. Next up, we needed to label the names or formula as alkenes or alkanes. So propene ending in -ene is an alkene. Butane ending in -ane is an alkane. Hexane ending in -ane is an alkane. Ethene ending in -ene is an alkene. C5H10, well 10 is double 5, so it's the general formula CnH2n for an alkene, so it's an alkene. C4H10, well 10 is double 4 plus 2, so that follows the general formula of CnH2n plus 2, so we're looking at an alkane here. Finally, C12H24, well 24 is double 12, so that's CnH2n, general formula of an alkene. The chemical test for alkenes and its result is as follows. The test is called adding bromine water, and you do need to shake it with the bromine water in there because normally the bromine water actually floats as a layer on top. So you need to shake it to get them mixed. If it changes from orange to colourless, not just goes colourless, from orange to colourless, then an alkene has been detected. Positive test result there. Always give the negative result as well. If it remains orange, no alkene is present. That might mean you've got an alkane, or it might mean you've got something else, but it means you haven't got an alkene. Right, finally, I want you to try to balance these cracking equations. So using the method that I described in the previous slides, try to find out what goes in all of these gaps. If it's one of the ones with a balancing number, I've already given it there for you. So all of these ones without balancing numbers, you've just got to write a formula in, not a formula and a balancing number. Okay then, so here's your answers. The first one, A, you should have got C6H12. For B, you should have got C5H10. For C, you should have got C8H18. D was C2H4. E was C2H4 as well. And then finally for F, we had to work out what the reactant was. You should have got C18H38. Well, thanks very much for watching this video, guys. I hope you enjoyed it and understood all of the content. I'll see you for the next one, where we're going to be looking at combustion reactions. See you then.